This situation presents an extremely dangerous electrical hazard requiring immediate attention. Exposed street light splices within an underground enclosure create a high risk of electrical shock and fire. The lack of proper insulation and protection around these splices means that any contact, whether accidental or due to equipment failure, can have severe consequences. It's crucial to understand the potential dangers involved when dealing with electrical infrastructure, especially in public areas. Firstly, the risk of electrical shock is paramount. The voltage present in street lighting circuits can be lethal. If the cover of the enclosure becomes energized due to contact with exposed conductors, anyone touching it could receive a dangerous, potentially fatal, electric shock. Secondly, the exposed splices are vulnerable to environmental factors. Moisture, corrosion, and physical damage can compromise the integrity of the connections, leading to short circuits, ground faults, and ultimately, electrical fires. Thirdly, the absence of a properly insulated and sealed enclosure allows for the possibility of unauthorized access and tampering. This increases the risk of accidental contact with live conductors and can also lead to vandalism or theft of electrical components. To mitigate these risks, several steps must be taken immediately. 1. The power to the street lighting circuit must be energized before any work is performed. This ensures the safety of the personnel involved in the repair. 2. A qualified electrician should inspect the entire installation to identify the extent of the damage and any other potential hazard. This includes checking the condition of the wiring, connectors, and any other associated equipment. 3. The exposed splices must be properly insulated and protected. This can be achieved by using approved splicing kits, heat shrink tubing, or other appropriate insulating materials. 4. The enclosure must be repaired or replaced to provide a secure and weatherproof barrier around the electrical components. This includes ensuring that the cover is properly secured and that there are no gaps or openings that could allow water or debris to enter. 5. The grounding system must be inspected and tested to ensure that it is functioning correctly. A properly grounded system provides a path for fault current to flow, which helps to protect against electrical shock and prevent equipment damage. 6. Once the repairs are completed, the circuit must be thoroughly tested to verify that it is safe and operating correctly. This includes checking the voltage, current, and insulation resistance to ensure that they are within acceptable limits. 7. A regular inspection and maintenance program should be implemented to prevent similar hazards from occurring in the future. This program should include periodic inspections of all street lighting enclosures, as well as routine testing of the electrical system. Understanding the electrical principles involved is essential for ensuring safety and preventing accidents. Voltage is the electrical potential difference between 2 points, and it is what drives the flow of electrical current. The higher the voltage, the greater the potential for electric shock. Current is the flow of electrical charge measured in amps. The amount of current that flows through the body determines the severity of the electric shock. Even a small amount of current can be lethal. Resistance is the opposition to the flow of electrical current measured in ohms. The higher the resistance, the less current will flow for a given voltage. Dry skin has a high resistance, but wet skin has a much lower resistance, making it easier for current to flow through the body. Ohm's law states the relationship between voltage, current, and resistance. Voltage equals current times resistance. This law is fundamental to understanding electrical circuits and is essential for troubleshooting electrical problems. Electrical safety codes and standards provide guidelines for the safe installation, operation, and maintenance of electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association, or NFPA, and the Institute of Electrical and Electronics Engineers, or IEE. The National Electrical Code, or NEC, is a widely adopted standard for electrical installations in the United States. It provides detailed requirements for wiring, grounding, overcurrent protection, and other aspects of electrical safety. Adhering to the NEC and other applicable codes and standards is essential for preventing electrical hazards and ensuring the safety of people and property. Grounding is a critical aspect of electrical safety. A grounding system provides a low-resistance path for fault current to flow back to the source, which helps to trip circuit breakers or fuses and to energize the circuit in the event of a fault. This prevents the buildup of dangerous voltages on equipment and reduces the risk of electric shock. Grounding also helps to protect against lightning strikes and other transient voltage surges. The NEC specifies detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the methods of grounding electrodes, and the bonding of metal enclosures. Overcurrent protection is another essential safety measure. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit. This prevents the overheating of conductors and reduces the risk of electrical fires. Circuit breakers are resettable devices that trip when the current exceeds a certain threshold. Fuses are one-time devices that melt and break the circuit when the current exceeds their rating. The NEC specifies the type and size of overcurrent protection required for different types of circuits and equipment. Electrical enclosures are designed to protect electrical equipment from the environment and to prevent accidental contact with live conductors. Enclosures are typically made of metal or plastic and are available in a variety of sizes and shapes. The NEC specifies the type of enclosure required for different locations and applications based on factors such as the presence of moisture, dust, and corrosive materials. Enclosures must be properly grounded and bonded to ensure electrical safety. Working with electricity can be dangerous, and it is essential to take precautions to prevent accidents. Always to energize the circuit before working on electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as rubber gloves and safety glasses. Never work on electrical equipment in wet or damp conditions. If you are not qualified to work on electrical equipment, call a qualified electrician. Regular inspection and maintenance of electrical systems is essential for preventing hazards and ensuring safety. Inspections should be performed by qualified electricians and should include a visual examination of the wiring, connections, and equipment, as well as testing of the grounding system and overcurrent protection devices. Maintenance should include cleaning and tightening connections, replacing worn or damaged components, and ensuring that all equipment is properly labeled and grounded. Specific considerations apply to street lighting circuits due to their exposure to the elements and public access. Firstly, ensure all wiring and connections are weatherproof and protected from moisture. Underground splices, in particular, require robust waterproof enclosures and connectors. Secondly, regularly inspect the condition of the poles, fixtures, and wiring for any signs of damage or deterioration. Thirdly, use tamper-resistant hardware and enclosures to prevent unauthorized access and vandalism. Fourthly, implement a regular maintenance schedule for replacing lamps and ballasts to ensure optimal lighting performance and energy efficiency. Fifthly, coordinate with local utility companies to ensure proper grounding and overcurrent protection for the street lighting circuits. Sixthly, document all inspections, maintenance activities, and repairs to maintain a comprehensive record of the street lighting system. In addition to the technical aspects, it's important to consider the legal and regulatory requirements related to electrical safety. Cities and municipalities have a responsibility to ensure the safety of their citizens and to comply with all applicable electrical codes and standards. Failure to do so can result in fines, lawsuits, and, most importantly, injuries or fatalities. Therefore, it's crucial for cities to invest in regular inspections and maintenance of their electrical infrastructure and to promptly address any hazards that are identified. The situation described highlights the critical importance of proactive electrical safety measures. By addressing the exposed streetlight splices immediately and implementing a comprehensive inspection and maintenance program, the risk of electrical shock, fire, and other hazards can be significantly reduced. Protecting public safety requires a commitment to electrical safety from both individuals and organizations. To expand on specific code references related to this scenario, several sections of the National Electrical Code, or NEC, are particularly relevant. NEC Article 314 addresses junction boxes, pull boxes, and handhole enclosures. Specifically, 314.27 covers outlet boxes and 314.30 deals with the securing and supporting of boxes. These sections outline the requirements for ensuring that electrical boxes are properly installed, supported, and protected from physical damage. In this case, the underground enclosure serving as a junction box for the streetlight splices must meet these requirements to ensure its structural integrity and prevent exposure of the electrical connections. NEC Article 300 provides general requirements for wiring methods and materials. Section 300.4, Protection against physical damage, is crucial in this scenario. It mandates that wiring be protected from physical damage, which is clearly not the case with exposed splices. Section 300.5, Underground installations, further details the requirements for underground wiring, including burial depth, protection from moisture, and the use of approved wiring methods. NEC Article 410 addresses luminaires, lamp holders, and lamps. While it primarily focuses on the installation and wiring of lighting fixtures, it also touches on the overall safety of lighting systems. Section 410.56, Attachment plugs, receptacles, and connectors, specifies requirements for connectors used in lighting circuits, ensuring they are suitable for the environment and protective from moisture and corrosion. NEC Article 250 covers grounding and bonding. This is perhaps the most critical article in relation to the described hazard. Proper grounding and bonding are essential for minimizing the risk of electric shock and ensuring that overcurrent protective devices operate effectively. Section 250.4, General requirements for grounding and bonding, outlines the basic principles of grounding and bonding, while subsequent sections provide more specific requirements for different types of systems and equipment. For example, 250.32 addresses grounding separately derived alternating current systems, and 250.92 covers bonding of equipment containing over 250 volts to ground. In addition to these specific articles, other sections of the NEC may also be relevant depending on the specific details of the installation. For example, Article 110, Requirements for electrical installations, provides general guidelines for safe electrical work practices, and Article 700, Emergency systems, may apply if the streetlights are part of an emergency lighting system. Understanding and applying these code requirements is essential for ensuring the safety of electrical installations and preventing hazards such as the one described. Regular inspections, proper maintenance, and adherence to the NEC are all crucial for protecting public safety and preventing electrical accidents. Further elaborating on practical solutions for rectifying the hazardous situation, several approaches can be considered depending on the extent of the damage and the specific requirements of the installation. One approach is to replace the existing underground enclosure with a new, properly rated enclosure that meets current safety standards. The enclosure should be constructed of durable, corrosion-resistant materials and should be designed to provide a secure and weatherproof barrier around the electrical connections. The enclosure should also be sized appropriately to accommodate all of the necessary wiring and splices without overcrowding. Another approach is to repair the existing enclosure if it is still structurally sound. This may involve patching any holes or cracks in the enclosure, replacing damaged hardware, and ensuring that the cover is properly secured. However, if the enclosure is severely damaged or corroded, replacement is usually the better option. Regardless of whether the enclosure is replaced or repaired, the exposed splices must be properly insulated and protected. This can be achieved by using approved splicing kits that are specifically designed for underground applications. These kits typically include waterproof connectors, insulating sleeves, and sealant to provide a reliable and long-lasting connection. Heat shrink tubing can also be used to insulate the splices, providing a tight and waterproof seal. In addition to insulating the splices, it is also important to protect them from physical damage. This can be achieved by encasing the splices in a protective conduit or sleeve. The conduit should be made of durable, corrosion-resistant materials and should be sized appropriately to accommodate the wiring and splices. The conduit should also be securely fastened to the enclosure to prevent it from being dislodged. Another important consideration is grounding. The grounding system must be properly installed and maintained to ensure that it is functioning correctly. This includes checking the condition of the grounding conductors, grounding electrodes, and bonding connections. If any of these components are damaged or corroded, they should be replaced immediately. Finally, it is important to conduct thorough testing after the repairs are completed to verify that the installation is safe and operating correctly. This should include testing the insulation resistance of the wiring, the continuity of the grounding system, and the operation of the overcurrent protection devices. Any problems that are identified during testing should be corrected before the installation is put back into service. By taking these steps, it is possible to rectify the hazardous situation and ensure the safety of the public. However, it is important to remember that electrical work should only be performed by qualified and experienced electricians who are familiar with the applicable codes and standards.